Hey everyone, this video is mainly for the H2 Math people because we're going to talk about parametric differentiation. By the name, we're looking at a parameter, right? So instead of just the usual y equals to fx or a equals to gb, we're looking at where each y and x are actually related to a common variable or a common parameter. So for instance, y equals to ft and x equals to gt. And another example would be a equals to, let's say, ki and b equals to ji. Okay, so of course in the case of y and x, you have common parameter t, and I is the common, and for a and b, the common parameter I. So how does this help us? So in parametric differentiation, we're able to represent the derivative or represent the rate of change of one variable to another with a common parameter. So we're able to, let's say we have dy dx, right? We are able to express this not in terms of y or x, right? But actually in terms of a common parameter that y and x share. How do we do that? Well, simply if you recall from the rate of change, we know that dy dx equals to dy dt divided by dx dt. All right, or basically replace a t with any variable and this will always hold true. So in this case, dy dt is basically f prime t, dx dt is basically g prime t, right? Because if y equals to ft, we will then have dy dt equals to f prime t, and of course the same thing can be said about x equals to gt. We have dx dt equals to g prime t. And of course the same can be said about a and b, dA dB equals to k prime I over j prime I. So if you notice, this derivative, dy dx, is no longer in y or x, it's in t. And this helps us, actually help us a lot more, especially when we cannot find a proper equation relating y and x, but we have to relate it to a common parameter, t, or whatever letter that's available. So let's give us an example. Let's say we have y equals to t squared minus 6t minus 1, and then with x equals to sine t. So obviously it's very difficult to express y and x is the same. So we do the easier way out. Parametric differentiation. So we have dy dx. What I do first is very simple. I differentiate y with respect to t first, so I get 2t minus 6. Then I differentiate dx, so I differentiate x, then I get back cosine t. You can do it the normal way. You can just find that, you can just switch this out, but it's a waste of time, and I do things fast. Okay, so we have dy dx equals to 2t minus 6 over cosine t. And I can stretch this even further to other applications of differentiation. This still represents a gradient at a certain point, let's say x, right? And you are able to use this to find, let's say, the tangents, your normals, or your stationary points. So if I want to find the stationary points for this, well, it's very simple. If this equals to 0, I have a stationary point at t equals to 3, right? Because the numerator must be equals to 0. So at t equals 3, what's the coordinate of the stationary point? We have x equals to sine 3, and y equals to, let's see if my math is correct, it will be minus 10. So this is how we can use parametric differentiation, and without actually knowing about x and y, how are they related directly, but we can actually relate it through a common parameter t. So yeah, this is just parametric differentiation.